Okay, but as I said, we need to move from bivariate analysis to multivariate analysis. And in the multivariate analysis, we ask the question, the like a revised kind of question, and is what happened in the relationship between x and y once we hold c constant? Does this relationship still work, or is it still in place or not? And this is what we call the partial effects. So we want the partial effects is the effect of x on y controlled by c, and the opposite, the effect of c on y controlled by x, controlled for x. I'm sorry, right? So I'm gonna say it again. Remember that we have these three variables. The partial effects are not only the relationship between x and y controlled for c, but also the relationship between c and y controlled for x, because there is this relationship, this potential relationship between these three variables. Okay? Okay. As you can remember, one of the key goals of this multivariate analysis and in general of research is to identify or confirm whether there is a relationship, like an additive, an interaction, or an spurious relationship between x or among x, y, and z. Okay? Let's remember what is an additive relationship. An additive relationship is when both x and y explain part of, x and c explain part of the outcome of interest. Okay? Both variables have an effect on y, but they don't necessarily affect each other. Okay? Not necessarily. We're going to talk about that later, but that's the idea of an additive relationship. There is also an interaction relationship in which x, basically the idea of an interaction relationship is that z works as a mediator between the relationship between x and y. And the effect of x and y operates through some levels of c and probably change in other levels of c or have no effect on some levels of c. Okay? And finally, there is an spurious relationship. And in a spurious relationship, x has no effect on y. And what was explaining what we thought that was a relationship in a bivariate analysis was actually c, because c was a confounder. And a confounder is a variable that affects x and affects y, and explain why, and create this artificial relationship between x and y. Okay? Okay. Again, we're going to have as a main tools tables and graphs. So the similar to the cross-tabulation is control tables. Basically, what we do is that we prepare cross tabs for each level of the control variable. Look at this example. This is the same example of the opinion on gun control and the relationship between partisanship and that opinion, right? What we do is to create basically two cross tabs, one for female and one for male. So we are controlling for gender, right? And what we want to do is to check whether the relationship between x and y still holds for both levels of C, right? So we can see here that the relationship still holds because female Democrats tend to support these policies of more control, more gun control than Republicans, as male Democrats do the same more than male Republicans, right? So control for gender, there is still a strong relationship between the type of party ID of a person and his or her opinion on gun control, okay? As I said, it's also interesting and relevant for the analysis to see what happened in the relationship between C and Y control for X. We see the other kind of relationship, and what we do here is to keep constant the type of partisanship. And for instance, we compare female Democrats, with male Democrats. And we see if, for instance, the hypothesis would be that female tend to be more supportive of stronger or stricter policies of gun control. We can see that that happens, like a female women tend to be more supportive of these policies than male Democrats. And similarly, female Republicans tend to be more supportive of these policies than male Republicans. Okay, so in this case, the relationship is also strong. Okay, so that's the first thing. We need to see if the effect of X and Y still holds, right? But what about interpretation? So we need to learn how to interpret this relationship. If this relationship is negative or positive, or what is this kind of relationship, right? In order to do that, we define a baseline category. For instance, if we want to analyze in terms of partisanship, we can say that Democrat is my baseline category, and we want to compare what happens if a person is Republican or independent in comparison with a Democrat person. Okay, that's the way that you analyze these results. And basically, you just subtract the effect of being Republican to being Democrat, but control for the gender, right? So what you have here is that the difference between female Democrat and female Republican in this case is positive, and it is a difference of 39 points, which is very high actually. And the difference between male Democrats and male Republicans is also very high, and in this case is 37 points. According to Pollock, because these effects are very similar, we can use an average to summarize the whole effect. So we can say the effect of being Democrat on the support to stricter gun control policies is on average 38 points, percentual points, control for gender, right? That's the way you read these results. But imagine that the results were not, like for instance, if the difference between male Democrats and male Republicans is very small, like 5 points. So you cannot use an average in this case. And what is better in this kind of cases is just to clarify the effect for each level of the control variable. So you say, for instance, for females, the effect is 38%, and for male, the effect is 5%. The effect of partisanship on my outcome of interest, okay? Another way that you can read these results is if the results are positive, you can say Democrats are more likely than Republicans to do something. And if the results are negative, you can see Republicans are less likely to support gun restrictions than Democrats. Okay, that's something very simple. It's about interpretation. Now, we move from interpretation, like at that basic level of what are the partial effects, and we move to identify what is the kind of relationship between, or the XYZ kind of relationship, right? And I think Pollock's heuristic or analytical method is very useful. You just basically ask and respond to 3 questions. First, after holding C constant, does X affect Y in at least one value of C? That's the first question. If not, you have an spurious relationship, right? If yes, you need to ask us the second question, which is the sign of the effect of X and Y the same in all values of C? If not, you have an interaction relationship, right? If yes, you have to answer the final question. And is the strength of the XY relationship the same in all values of C? If not, again, you have an interaction relationship. If yes, you have an additive relationship. Okay? This is very simple and you can use it. It's like a very intuitive, and you can use it for your analysis and like in general in statistics. Okay, so we have tables, but we also have figures to try to identify these relationships. And one of the most powerful figures is the line charts. The line charts are very useful, and in general, as you have seen, figures tend to be more useful than tables to identify very quickly these relationships. So you can see here that there is an additive relationship between partisanship and the public opinion on gun restriction. The red line is the aggregated version, or what might be the relationship between X and Y without seeing Z. And the black line is basically what happened with this relationship when you control for female, and the dash line is when you have like a male Democrats and male Republicans, and you can see that there is an additive relationship here, right? Okay, this is an example of an interaction relationship, because in this example, you can see that the effect. Okay, let's see this example. Okay, this is in the basically the relationship between abortion opinion and party ID. It's like at the opposite. In this case, is the idea that people who think that abortion should be legal in every case, for instance, tend to support more the Democratic Party, right? But this is mediated by the role of how salient is the issue of abortion for this person. Okay, if that for that person, okay, that's the basic scenario. So without considering the how salient is this topic for the person, we can see that the people who think that abortion should be always permitted tend to vote more for the Democratic Party than people who think that the abortion should be never permitted. Okay, so the relationship is positive. But when we control by the salience, we can see that the people who has or for who this topic is not very salient, the relationship between abortion opinion and party ID tends to be weaker than for the people who think that this topic is very important. For that people, the relationship is very strong. For that reason, I'm sorry, what we have here is an interaction relationship. Okay? Okay, so for mean comparison, when we have again a dependent variable that is at the interval level or the ratio level, we can estimate the mean, and we do this similar thing of what we did in the mean comparison tables, but in this case we control by the values of C. So basically what we do is that in the columns are defined by the values of the control variable, and the rows are again defined by the independent variable. And we basically see again what happened when there is a change in the values of the independent variable, control for each value of the control area. What is this example? Is basically the mean immigrants feeling thermometer scores, and the idea that probably what is the relationship between gender and these thermometers, control for the age. Okay, this is just a toy example. Okay, so those are the tools that we have to study these multivariate relationships and bivariate relationships. Okay, now we're gonna move to a kind of technical level. What should we use? Should we use tables, or should we use figures, or should we use both? Right? And there are people who think that we should use graphs or figures instead of tables because figures tend to be like a more powerful to communicate the results of an empirical analysis. Like a very quick, you see that the relationship is additive or not, that is negative or positive, that is linear or non-linear, or this kind of rough relationships can be very easily identified with a graph. Even more is so much easier than with a table, right? For that reason, I think sometimes it's very powerful to use figures to present the results of a statistical analysis. And actually, some authors such as Kastelek and Leoni, for instance, make a very strong case for using graphs instead of tables. Look at this example of how they encourage us to use mosaic plots instead of cross tabulations. And honestly, this mosaic plot is beautiful. Like it's very easy to see the difference between two groups related or based on the values of, in this case, electoral system and government partisanship. So it's very simple to see this relationship even more than with the table, right? Especially if you are a graphical person, visual person, it's very simple to get the idea very quick, okay? This is also a good example how you should use, or you can use, dot plots to present summary statistics such as the mean and the standard deviation rather than tables. This is a very cool example because what you can see here is that, for instance, in the variable size, you can see that the mean is in this case 3 point something, 13. But what is interesting is how we represent the standard deviation. The standard deviation is a measure of precision. And look at here, because the standard deviation is very high, it's 1.49, the chances to be farther from the mean are higher than, for instance, in the case of, I think it's political agreement, in which the standard deviation is very small. It is, I'm sorry, no, the better is political agreement, in which is 0.41, right? So in the political agreement, the target is smaller than in the case of size. I don't know. We're going to talk a little bit more about this idea, but the important point here is that dot plots can convey or can communicate this idea of the mean and the standard deviation probably in a stronger manner than the tables, right? And there are other kind of figures that we can use to represent these results, and especially nowadays in the case of linear regressions and this kind of more complex statistical analysis, in which tables are difficult to read to some extent and to interpret. Figures are much more the golden standard to present these results. Nowadays, we tend to use figures to represent this, or to present these results and in a more powerful way than with tables, okay? Okay, but what is the case of tables and against graphs? First of all, sometimes it's harder to prepare figures than to prepare tables. And it used to be very simple in some statistical packages such as Stata, but you will see that this is probably not always the case in R. It's not more difficult than preparing a graph, but it's not super simple as just write a function, okay? But yeah, to some extent, preparing graphs is a little bit trickier and a little bit more complicated, but that complexity is sometimes related with the aesthetical part of the figure, like how to put labels, how to change the colors, how to change the geometric objects such as points, lines, and these kind of things. It's much more that than the bare bones of the graphic. So prepare the graphic is kind of simple, but make this graphic beautiful is what is trickier and requires more like a technical skills, okay? But the real case of tables against graphs is that sometimes with graphs you can, depending on how you prepare the graphs, and even in a way that is innocent to some extent, you can manipulate, or you can shape the results in a way that support your case, but is maybe not true to some extent. And look at this example. This is from Gravater et al. And basically what happened here is that you can see the number of homicides from 2013 to 2016, and because you omitted part of the values in the y-axis, you can think that the change from 2013 and 2015 was higher than what actually was. Like for instance, it seems that the change between 2012 and 2015 was very high difference, but when you use all the values of the y-axis, you can see that that change is very small. So that can happen with the graphs, right? That's one of the risks of using graphs. And especially like a tables can give us, especially with descriptive statistics, tables give us grounded results, like precise numbers that you can use to make a strong case about the change between one variable and, I don't know, the effect of one value of the independent variable in the dependent variable. And you will see that the problem with descriptive statistics is that results are not always as strong as the example of partisanship and public opinion on a gun restriction policy or something like that. Sometimes the nuances are very difficult to interpret. Sometimes the differences are very small. And for that reason, we need to move to more sophisticated kind of methods to see the change, for instance, instead of 30 points, percentile points, to the change in 2 points is significant in statistical terms or not. And we're going to learn what does this statistical concept mean. But for now, what I want to say is that sometimes tables are stronger to show these very nuanced differences between two variables that sometimes graphs cannot help us to identify these relationships or to interpret these kind of effects. Okay, so my verdict is both kind of tools are useful and relevant. Use both. Probably if you're gonna write an article or you're gonna write something in the future, you're not gonna have a space for many tables or many figures. But what you can do is just use the figures or use the tables or whatever you prefer, and in the appendix of that document put the other kind of tool, right? But the thing is, both are useful, so use them both. Okay, that's all for today. It was a more simpler kind of lecture, but I think this is very useful as a first step to move forward to the more complex kind of contents that we're gonna see with inferential statistics, and hopefully we have enough time to see linear regression. That is my goal. So these things will make more sense and will be useful for you. Okay, as usual, write the questions in the discussion board number 4, and I'm gonna use those questions, especially if these are like a more conceptual questions. I'm gonna prepare materials if it is necessary to respond to those questions. Okay, keep in mind this. The idea is that at the end of this lecture, you will be able to use tables and figures to identify and interpret zero-order effects and partial effects in bivariate and multivariate analysis. You will be able as well to use these tools to identify and interpret spurious interaction and additive relationships, and you also will be aware of the strengths and limitations of tables and graphs in descriptive statistics. Thank you so much for everything. Bye.